Look up. What do you see? Perhaps a vast inky blackness sprinkled with stars, or maybe the glow of city lights obscures all but the brightest celestial objects. Hidden from view lies a universe teeming with galaxies. These cosmic cities are vast collections of stars, gas, and dust. For millennia, humans have gazed upon the night sky. Ancient civilizations wove tales of gods and monsters among the stars. With powerful telescopes, our cosmic perspective shifted. Faint patches of light were revealed to be galaxies, each a swirling metropolis of billions of stars. Galaxies follow an intricate cosmic dance drawn by gravity. They form vast cosmic structures stretching across light years. Galaxies interact, collide, and merge, spanning billions of years. Our Milky Way is one island in this cosmic archipelago, a barred spiral galaxy, home to billions of stars. From our vantage point, we see the universe's diversity. Each galaxy, regardless of its size or shape, is a marvel of cosmic architecture. At their hearts lie supermassive black holes, gravitational behemoths millions or even billions of times the mass of our Sun. These black holes shape the evolution of their host galaxies. Stars, gas, and dust orbit in a delicate balance. The stars within a galaxy are organized into intricate structures. Their distribution reflects the galaxy's history and the forces that have shaped it. Spiral galaxies, like our own Milky Way, have graceful spiral arms. Elliptical galaxies are relatively devoid of gas and dust, dominated by older stars. Galaxies harbor a mysterious and invisible constituent dark matter. This elusive substance makes up the vast majority of a galaxy's mass. Its gravitational influence holds galaxies together. Dark matter's presence is inferred from its gravitational effects. The distribution of dark matter plays a crucial role in galaxy formation. Dark matter formed a vast cosmic web in the early universe. Understanding dark matter is a pressing challenge in modern astrophysics. Galaxies are dynamic, evolving systems. Over billions of years they grow, change, and interact with their surroundings. Star formation drives galactic evolution. Gravity causes gas clouds to collapse, forming stars. In spiral galaxies, star formation is concentrated in the arms. Elliptical galaxies have low star formation rates. Massive stars end in supernova explosions, seeding heavy elements. Galaxies, while separated by vast distances, are not isolated islands in the cosmos. They are engaged in a cosmic ballet, their movements governed by the relentless pull of gravity. Galaxies are drawn together into clusters and superclusters, forming a vast cosmic web. Within these clusters, galaxies interact, shaping their appearances and destinies. Tidal forces can distort galaxy shapes, drawing out long streams of stars and gas. These interactions can trigger bursts of star formation, igniting a frenzy of stellar birth. In some cases, galactic interactions can be far more dramatic. When two galaxies collide, their stars rarely collide directly, but gas and dust do. These collisions trigger shock waves, compressing gas clouds and igniting star formation. The merging galaxies light up with the birth of millions of new stars. Galactic collisions can strip away gas and dust, transforming spiral galaxies into elliptical ones. They can also trigger the growth of supermassive black holes at the centers of galaxies. The remnants of these mergers are seen in distorted shapes and unusual stellar populations. Galactic archaeology. Studying galaxies is like piecing together a cosmic puzzle, using light to reconstruct their history. Observing galaxies at different distances helps trace their evolution over billions of years. Spectroscopy reveals a galaxy's chemical composition and star formation history. Gravitational lensing magnifies distant galaxies, aiding detailed study. These techniques build a picture of galaxy evolution over cosmic time. Our place in the cosmos. In the grand scheme of the cosmos, our galaxy, the Milky Way, is but one among billions. Our understanding of galaxies is connected to our place within the Milky Way. Observations of other galaxies are shaped by our perspective from within our own. From our vantage point, we have a limited view of our galaxy's structure. Dust clouds obscure our view of the galactic center. Through careful observations, astronomers are piecing together a more complete picture. They have mapped the distribution of stars and gas, revealing its spiral structure. They have studied the motions of stars and gas clouds, inferring a supermassive black hole at the center. Our understanding of the Milky Way provides context for studying other galaxies. By comparing the Milky Way to other galaxies, we identify common features and unique characteristics. The Milky Way serves as a cosmic laboratory for testing theories of galaxy formation and evolution. A journey begins. Galaxies are more than just distant objects in the night sky. They are cosmic cities, teeming with activity, their stories intertwined with the history of the universe itself. By studying galaxies, we are not just exploring the cosmos, we are unraveling the story of our own origins. We are made of star stuff, the atoms in our bodies forged in the cores of stars that lived and died long ago in galaxies scattered throughout the universe. In this documentary, we will embark on a journey to explore the fascinating world of galaxies. We will delve into their birth, their lives, and their deaths. We will uncover the invisible forces that shape them and the processes that drive their evolution. We will witness the beauty and violence of galactic collisions, the quiet majesty of spiral galaxies, and the enigmatic glow of active galactic nuclei. Our journey will take us to the edge of the observable universe, where we will glimpse the faint light of the earliest galaxies, providing us with clues to the conditions in the early universe. We will peer into the hearts of galaxies, where supermassive black holes lurk, their gravitational pull shaping the destinies of billions of stars. And we will explore the mysteries of dark matter, the invisible hand that guides the evolution of galaxies. Join us as we embark on this cosmic adventure, a journey to unravel the secrets of the universe's most magnificent creations, its galaxies. In the beginning there was nothing, no stars, no galaxies, no planets, no light. Then, in an instant, everything changed. The universe erupted into existence in a cataclysmic event we call the Big Bang. Time and space were born, and with them, the seeds of structure that would eventually give rise to galaxies. As the universe expanded and cooled, energy began to condense into matter. Subatomic particles coalesced into protons and neutrons, the building blocks of atomic nuclei. Tiny fluctuations in density, amplified by gravity, would serve as the seeds from which galaxies would sprout. Gravity, the architect of the cosmos, began to exert its influence on the nascent universe. Regions of higher density exerted a stronger gravitational pull, drawing in more matter. This amplified density differences, leading to the formation of galaxies. As the universe expanded, it cooled, allowing matter to decouple from radiation. This transition released the cosmic microwave background radiation, a relic of the Big Bang. These fluctuations, amplified by gravity, formed the cosmic web of galaxies we see today. The early universe, though now transparent to light, was still a far cry from the starlit sky we see today. The first stars had yet to ignite, and the universe was plunged into a cosmic dark age. Gravity drew matter together, amplifying density fluctuations seeded in the Big Bang. Dark matter, a mysterious substance, dominated the early universe. Its presence is inferred from gravitational effects on visible matter. Dark matter played a crucial role in galaxy formation. Its gravity created halos, pulling in ordinary matter and shaping galaxies. Within the dense, hot cores of these primordial gas clouds, gravity continued to compress the gas, driving up temperatures and pressures to unimaginable extremes. Eventually, conditions became so extreme that hydrogen atoms, the simplest and most abundant element in the universe, began to fuse together, releasing a tremendous amount of energy in the process. The first stars were born. These first stars were very different from the stars we see today. They were massive, hundreds of times the mass of our sun, and incredibly luminous, shining with the brilliance of millions of suns. Their lifespans, however, were short, lasting only a few million years before they exhausted their nuclear fuel and exploded as powerful supernovae. The deaths of these first stars had a profound impact on the evolution of the universe. The intense heat and pressure generated by their supernova explosions forged heavier elements, such as carbon, oxygen, and iron, scattering them into the interstellar medium. These elements, absent in the early universe, would become the building blocks of planets, moons, and life itself. The supernovae also injected energy and momentum into the surrounding gas, driving shockwaves that triggered the formation of more stars. The cosmic dawn had begun, and with it, the era of galaxy formation. The formation of galaxies was not a uniform process. It was a chaotic and complex dance of gravity, gas dynamics, and stellar feedback. Gas fell into dark matter halos, forming rotating disks of gas and stars. Angular momentum shaped these early galaxies. Collapsing gas clouds spun faster, flattening into disks. This rotation prevented direct collapse, forming disks. Stars formed, shaping the surrounding gas and dust. Supernova explosions regulated star formation. Dark matter sculpted diverse galaxy shapes. Some galaxies, like the Milky Way, formed spiral arms. Others evolved into massive elliptical galaxies. Some remained small and irregular, reflecting a turbulent past. As the universe expanded, galaxies clustered together, forming a cosmic web. These clusters interacted, shaping their appearances and triggering star formation. Galactic collisions could strip away gas, quenching star formation and transforming galaxies. They could also trigger the growth of supermassive black holes. The remnants of these mergers reveal their tumultuous pasts. The galaxies we see today are the products of billions of years of cosmic evolution. They are vast, complex systems shaped by the interplay of gravity, gas dynamics, and stellar feedback. By studying galaxies, we are not just exploring the distant universe. We are peering back in time, uncovering the history of the cosmos itself. The light from distant galaxies has taken billions of years to reach us, offering a glimpse of the universe as it was in its youth. By observing galaxies at different distances, and therefore at different points in cosmic time, astronomers can trace the evolution of galaxies over billions of years, piecing together the story of how these cosmic metropolises came to be. The study of galaxies is a journey of discovery, a quest to understand the universe's most magnificent creations. As we continue to explore the cosmos with ever more powerful telescopes, we are constantly uncovering new mysteries and pushing the boundaries of our knowledge. The story of galaxies is a story that is still being written, and we are privileged to be witness to its unfolding. Galaxies. Vast islands of stars, gas, and dust, scattered across the cosmos like glittering jewels on a velvet canvas. each a bustling metropolis, teeming with activity, its inhabitants engaged in a cosmic ballet of birth, life, and death. The Milky Way, our galactic home, contains hundreds of billions of stars, each a fiery furnace generating energy through nuclear fusion. And the Milky Way is just one of billions of galaxies, each with its own unique history and story to tell. Within the swirling disks of spiral galaxies and the diffuse halos of elliptical galaxies, stars are born. In cold, dense molecular clouds, gravity gathers hydrogen, helium, and trace elements. These clouds span light years and glow with ethereal radiance. Gravity fragments the cloud into clumps, heating their cores. Nuclear fusion ignites, forming a new star. The star's light balances gravity and radiation pressure. Star formation is not a solitary endeavor. Stars are born in clusters from the same molecular cloud. These clusters are cosmic nurseries, cradling newborn stars. Stars within a cluster span a range of masses. Massive stars burn brightly but live short lives. Low-mass stars shine modestly but endure for billions of years. Massive stars influence their surroundings profoundly. Their radiation creates glowing nebulae. Stellar winds carve out vast cavities in the gas. Massive stars explode as supernovae, seeding the interstellar medium with heavy elements. These elements form future stars and planets, enriching the universe's chemical diversity. Galaxies are not static entities frozen in time. They are dynamic, evolving systems, their appearance is shaped by a complex interplay of internal and external forces. Over billions of years, galaxies grow, change, and interact with their surroundings, their stories etched in the very fabric of spacetime. One of the most dramatic ways in which galaxies evolve is through mergers, cosmic collisions that can reshape entire galaxies, triggering bursts of star formation, fueling the growth of supermassive black holes, and transforming spiral galaxies into elliptical galaxies. As two galaxies approach each other, their gravitational fields interact, distorting their shapes and drawing out long streams of stars and gas known as tidal tails. These tidal tails, stretching across hundreds of thousands of light years, are a testament to the immense gravitational forces at play during a galactic merger. As the galaxies continue to merge, their gas clouds collide, triggering shockwaves that ripple through the interstellar medium. These shockwaves compress gas clouds, igniting a frenzy of star formation, illuminating the merging galaxies with the light of millions of newborn stars. From our vantage point on Earth, we are treated to a breathtaking view of the Milky Way, our galactic home. It is a barred spiral galaxy with hundreds of billions of stars, gas, and dust. At its heart lies a supermassive black hole, millions of times the mass of our Sun. The Milky Way is part of the local group, including the Andromeda Galaxy. In a few billion years, they will merge to form Milkomeda. Galaxies are not just static collections of stars. They are dynamic, evolving systems, their inhabitants engaged in a cosmic ballet of birth, life, and death. Stars are born in stellar nurseries, live out their lives, and eventually die, some quietly, others in spectacular supernova explosions that enrich the interstellar medium with heavy elements. Galaxies themselves interact and merge, their collisions triggering bursts of star formation and shaping their morphologies. And throughout it all, the invisible hand of dark matter guides their evolution, shaping their halos, influencing their rotations, and orchestrating their interactions. The study of galaxies is a journey of discovery, a quest to understand the universe's most magnificent creations. As we continue to explore the cosmos with ever more powerful telescopes, we are constantly uncovering new mysteries and pushing the boundaries of our knowledge. The story of galaxies is a story that is still being written, and we are privileged to be witness to its unfolding. In the vast cosmos, galaxies are not solitary wanderers. They engage in a cosmic ballet, governed by gravity. Sometimes, galaxies collide in space. These collisions shape galaxies, trigger star formation, and fuel black holes. Imagine two spiral galaxies, adorned with glowing nebulae, separated by millions of light years, but gravity draws them together. Slowly, their paths converge. Gravitational fields interact, creating tidal tails. Tidal tails stretch across light years. Galaxies are reshaped and elongated. The encounter is a slow dance. Eventually, their dance becomes frenetic. As the two galaxies plunge towards each other, their gas clouds collide head-on, triggering shock waves that ripple through the interstellar medium. The shock waves compress the gas clouds, driving up their temperatures and densities to extreme levels. Within these compressed gas clouds, the seeds of new stars are sown. The increased density and temperature create ideal conditions for star formation, triggering a cosmic baby boom. The merging galaxies erupt with the light of newborn stars, their spiral arms ablaze with stellar nurseries. This burst of star formation, known as a starburst, can temporarily outshine the combined light of all the other stars in the merging galaxies. It is a testament to the transformative power of galactic collisions. But the birth of new stars is not the only consequence of these cosmic collisions. Deep within the hearts of the merging galaxies, supermassive black holes stir from their slumber. Drawn together by the same gravitational forces, these black holes spiral towards each other. Their paths converge in a cosmic dance of death and destruction. As the galaxies continue their gravitational tango, their shapes become increasingly distorted, their spiral arms stretched into long, arcing tidal tails. These tidal tails, composed of stars, gas, and dust, are flung out into intergalactic space. They are a testament to the immense gravitational forces at play during a galactic merger. Some tidal tails stretch out for hundreds of thousands of light years, forming vast bridges of stars and gas. Others form loops and arcs that encircle the merging galaxies like celestial fireworks. And still others are completely ejected, flung out into intergalactic space to wander the cosmos as solitary stellar streams. These tidal tails and stellar streams are more than just visually stunning phenomena. They are valuable tools for astronomers, providing insights into the dynamics of galactic mergers. By studying the motions of stars and gas within tidal tails, astronomers can reconstruct the history of galactic mergers. The stars within tidal tails provide a unique window into the properties of the galaxies from which they were torn. They can have different chemical compositions and ages, providing astronomers with a fossil record of the stellar populations of the original galaxies. As the merging galaxies spiral closer together, their gas clouds continue to collide, triggering intense bursts of star formation. The rate of starbirth can increase dramatically, transforming the merging galaxies into luminous infrared galaxies. This frenzied pace of star formation, however, is unsustainable. The gas clouds are quickly depleted, consumed in a cosmic conflagration of stellar birth. Within a few 100 million years, the starburst begins to fade. But while the starburst may be ending, the activity at the centers of the merging galaxies is just heating up. The supermassive black holes, drawn together by their mutual gravitational attraction, are now spiraling towards each other. As the black holes approach each other, they begin to devour the surrounding gas and stars. The infalling material forms a swirling accretion disk around each black hole, heated to millions of degrees. The accretion disks emit intense radiation, transforming the merging galaxies into active galactic nuclei. Our own galaxy, the Milky Way, is not immune to the cosmic dance of galactic mergers. Astronomers believe that the Milky Way has undergone numerous mergers throughout its history, and the Milky Way is not done merging. Observations of our nearest large galactic neighbor, the Andromeda Galaxy, reveal that it is on a collision course with the Milky Way. The two galaxies are destined to collide in about 4 billion years. The collision will be a spectacular event, a cosmic light show that will unfold over billions of years. The two galaxies will initially pass through each other, triggering bursts of star formation, but their mutual gravitational attraction will eventually pull them back together for a second, more violent encounter. During this second encounter, the two galaxies will merge in earnest. The supermassive black holes at their centers will eventually merge, sending gravitational waves rippling through space-time. The Milky Way's past mergers have left behind telltale signs in its structure and stellar population. Astronomers have identified several streams of stars in the Milky Way's halo that are thought to be the remnants of past galactic mergers. These stellar streams allow astronomers to piece together the history of the Milky Way's growth and evolution. One such stream, the Sagittarius stream, is thought to be the remnants of a dwarf galaxy torn apart by the Milky Way's gravity. The Sagittarius stream forms a giant loop around the Milky Way, its stars stretched out across more than 100,000 light-years. Another stream, the Helmi stream, is thought to be the remnants of a globular cluster disrupted by the Milky Way's gravity. The Helmi stream is much fainter, but still visible in the Milky Way's halo as a faint trail of stars. These stellar streams, along with other evidence, suggest that our galaxy has experienced a turbulent past, and the future holds more of the same as the Milky Way prepares for its ultimate collision with the Andromeda Galaxy. Galactic collisions are not isolated events. They are a fundamental process that has shaped the evolution of galaxies throughout the history of the universe. In the early universe, when galaxies were closer together, collisions were much more common. These early collisions played a crucial role in driving the growth of galaxies, triggering bursts of star formation and fueling the growth of supermassive black holes. Even today, billions of years after the Big Bang, galactic collisions continue to shape the universe we see around us. The Antennae galaxies, located about 70 million light-years from Earth, are a spectacular example of two galaxies caught in the act of merging. The collision between these two galaxies has triggered a frenzy of star formation, illuminating them with the light of millions of newborn stars. Galactic collisions are a testament to the dynamic nature of the universe. They are also a source of awe and wonder, a glimpse into the powerful forces that have shaped the universe we see around us. In the grand tapestry of the cosmos, galaxies blaze with the brilliance of billions of stars. Yet even these titans of the universe are not immune to the relentless march of time. Like aging stars, galaxies too experience a twilight, a gradual decline that marks the end of an era of star formation. The death of a galaxy is not a sudden cataclysmic event, but rather a slow, drawn-out process that unfolds over billions of years. It is a gradual fading away, a dimming of the lights as the galaxy's supply of star-forming fuel is exhausted. This process of galactic aging can be triggered by a variety of factors, both internal and external. Some galaxies exhaust their supply of star-forming gas in a frenzy of early star formation. Others are stripped of their gas by interactions with their galactic neighbors. And still others fall victim to ram pressure stripping, where the hot, diffuse gas that permeates galaxy clusters blows away the cooler, denser gas that galaxies need to form new stars. The most readily available fuel for star formation is hydrogen gas, the most abundant element in the universe. This gas, often found in vast, cold clouds within galaxies, is the raw material from which stars are born. As gravity draws this gas together, it collapses and heats up, eventually reaching temperatures and densities sufficient to ignite nuclear fusion in their cores. However, over time, a galaxy's supply of hydrogen gas can become depleted. Each new generation of stars consumes a portion of the available gas, locking it away in stellar cores. And as the galaxy ages, its ability to replenish its gas supply from external sources can also decline. As a galaxy's gas supply dwindles, its rate of star formation slows. The once bright spiral arms begin to fade, their stellar nurseries growing quiet. The galaxy's overall color begins to shift from the blue hues of young, hot stars to the redder tones of older, cooler stars. This transition from a blue star-forming galaxy to a red, quiescent galaxy is a gradual one, but it is a one-way street. Once a galaxy has exhausted its supply of star-forming fuel, it is unlikely to reignite star formation on a large scale. As a galaxy's star formation rate declines, its overall luminosity also decreases. The massive hot stars that once dominated its light output have long since exploded as supernovae, leaving behind a population of fainter, longer-lived stars. These stars, mostly red dwarfs and white dwarfs, emit far less light than their massive brethren, causing the galaxy to fade in brightness. The galaxy's morphology also changes as it ages. Spiral galaxies gradually lose their spiral structure as their gas supply dwindles. Their arms become less defined, their star formation rates decline, and their overall shapes become more diffuse and rounded. In some cases, these aging spiral galaxies may eventually evolve into lenticular galaxies. Lenticular galaxies have disks like spiral galaxies but lack the prominent spiral arms and active star-forming regions. Elliptical galaxies, on the other hand, are thought to be the end product of multiple galactic mergers. These massive spheroidal galaxies are composed mostly of old red stars and contain very little gas and dust. While the stars within a dying galaxy may be fading, the supermassive black hole at its center can continue to exert a powerful influence. As the galaxy ages and its central regions become more densely packed with stars, the supermassive black hole can capture more material. As material spirals into a supermassive black hole, it forms an accretion disk, heated to millions of degrees. This accretion disk emits intense radiation, making the galaxy's central regions shine brightly. In some cases, the energy emitted by the accretion disk can drive powerful outflows of gas. These outflows, known as active galactic nuclei, AGN, can extend for hundreds of thousands of light-years. While AGN activity is often associated with young, actively star-forming galaxies, it can also occur in older, quiescent galaxies. In these cases, the AGN activity is thought to be triggered by the influx of fresh gas and stars into the galaxy's central regions. As stars die, they leave behind white dwarfs, neutron stars, and black holes. These remnants are faint and difficult to detect. White dwarfs are remnants of low-mass stars. They shed outer layers, leaving a dense core. White dwarfs emit only a tiny fraction of their former light. Neutron stars are remnants of massive stars. Supernovae compress cores into neutrons. Neutron stars are incredibly dense. They emit intense radiation. Black holes form from the collapse of massive star cores. Their gravity is so strong, not even light escapes. We infer black holes from their gravitational effects. As galaxies age and their star formation rates decline, the universe as a whole will gradually become dimmer. The bright star-forming galaxies that dominate the cosmos today will eventually fade away, leaving behind a population of faint, quiescent galaxies populated by stellar remnants. This process of cosmic dimming is already underway. Astronomers have observed that the star formation rate in the universe peaked several billion years ago and has been declining ever since. This decline is expected to continue as the universe ages and its supply of star-forming gas dwindles. In the far-distant future, trillions of years from now, the universe will be a much different place than it is today. The stars will have long since burned out, leaving behind a scattering of stellar remnants, white dwarfs, neutron stars, and black holes. These remnants will gradually cool and fade, their faint glow eventually extinguished by the expansion of the universe. The universe will become a cold, dark, and empty place, its once brilliant tapestry of stars and galaxies reduced to a smattering of faint embers. This is the ultimate fate of the universe as we know it, a slow and inevitable decline into darkness and silence. Our journey through the universe reveals the beauty and complexity of galaxies, those swirling metropolises of stars, gas, and dust. We've witnessed their birth, evolution, and eventual demise. Yet, our exploration would be incomplete without delving into dark matter. Dark matter does not interact with light. It neither emits nor absorbs light, making it invisible. Its presence is revealed through gravitational effects on visible matter. The story of dark matter is one of cosmic detective work. It has captivated astronomers for decades. Our first hints came from observations of galaxy clusters. These clusters provided the first evidence of hidden matter. In the 1930s, Swiss astronomer Fritz Zwicky discovered that galaxies in the Coma cluster were moving too fast for the visible matter present. He proposed the existence of dark matter, an unseen form of matter providing the extra gravity. Initially met with skepticism, Zwicky's idea gained support as more evidence accumulated. Observations of galaxy rotation curves and gravitational anomalies confirmed the presence of dark matter. The cosmic microwave background radiation, discovered in 1964, is the faint afterglow of the Big Bang. It provides a snapshot of the universe 380,000 years after the Big Bang. The CMB is remarkably uniform, with tiny temperature fluctuations. These fluctuations reflect early density variations, the seeds of galaxies. Analyzing these patterns revealed the influence of dark matter. Dark matter shaped the density fluctuations in the early universe. CMB observations, combined with galaxy data, confirm dark matter's existence. The prevailing theory is that dark matter is composed of weakly interacting massive particles, or WIMPs, hypothetical particles that interact with ordinary matter only through the weak force and gravity. WIMPs, if they exist, would have been produced in the early universe and would have survived to the present day, forming vast, invisible halos around galaxies. Astronomers are actively searching for WIMPs using a variety of techniques, including underground detectors designed to detect the faint recoil of atomic nuclei when struck by a WIMP, and particle accelerators that attempt to create WIMPs by smashing together subatomic particles at incredibly high energies. While the search for WIMPs continues, astronomers are also exploring alternative explanations for dark matter. Some theories propose the existence of new undiscovered particles, while others suggest modifications to our understanding of gravity. However, despite decades of research, no definitive evidence for any of these alternative theories has been found. The mystery of dark matter is a profound one, challenging our understanding of the universe at its most fundamental level. It is a reminder that there is still much that we do not know about the universe we live in, and that the cosmos is full of surprises waiting to be discovered. Despite its elusive nature, astronomers have developed ingenious techniques to map the distribution of dark matter in the universe. One such technique, known as gravitational lensing, takes advantage of the fact that gravity bends the path of light. When light from a distant galaxy passes by a massive object, such as a galaxy cluster, its path is bent by the cluster's gravity. This bending of light, known as gravitational lensing, can act like a cosmic magnifying glass, distorting and amplifying the light from background galaxies. By analyzing the distorted shapes of background galaxies, astronomers can map the distribution of mass in the foreground cluster, including both visible matter and dark matter. Gravitational lensing has revealed that galaxy clusters are embedded in vast halos of dark matter, extending far beyond the visible extent of the cluster's galaxies. Another technique for mapping dark matter is to study the motions of galaxies within galaxy clusters. The velocities of galaxies within a cluster are influenced by the cluster's gravity, which is dominated by dark matter. By analyzing the velocities of galaxies in a cluster, astronomers can infer the distribution of dark matter within the cluster. Dark matter forms a vast cosmic web, a network of filaments and voids. Galaxies are found along these filaments, drawn by dark matter's gravity. Dark matter shaped the universe, from the first stars to today's galaxies. The quest to understand dark matter drives astronomers to build powerful telescopes. The universe, a vibrant tapestry of galaxies, is slowly dying. This slow decline is an inevitable consequence of the laws of physics. The universe is expanding, cooling, and its energy density is decreasing. Star formation is declining as raw materials dwindle. The peak of star formation occurred billions of years ago. New stars are becoming increasingly rare. As the universe ages, galaxies will undergo a slow transformation. Spiral galaxies will fade as star formation dwindles. Their arms will become less defined. Galaxies will become more diffuse and rounded. Elliptical galaxies will dominate, with older stars. They will become more quiescent. The universe will fade to a dull red glow. The night sky will darken, with faint red dwarfs. While star formation will decline across the universe, galactic interactions and mergers will continue, driven by the relentless pull of gravity. However, these interactions, once a source of renewed star formation as colliding gas clouds triggered bursts of stellar birth, will become increasingly sterile affairs in a universe starved of star-forming fuel. Galaxies, desperate for resources, will cannibalize each other, stripping away their remaining gas and dust, but with little new star formation resulting from these encounters. The larger galaxies, their gravitational pull enhanced by past mergers, will consume their smaller companions, growing ever larger but also ever dimmer as their stellar populations age and their star formation rates dwindle. These interactions, once a source of galactic rejuvenation, will become desperate struggles for survival in a universe where the resources for growth and renewal are becoming increasingly scarce. The universe, once a dynamic and ever-changing tapestry of galaxies, will gradually settle into a more static state, its inhabitants locked in a slow dance of gravitational interaction, but with little change or evolution over time. As the universe expands and cools, the last stars will burn out, leading to a cosmic dark age. Only faint remnants like white dwarfs, neutron stars and black holes will remain. White dwarfs will cool to black dwarfs, fading away. Neutron stars will spin down, their pulsars falling silent. Black holes will dominate but eventually evaporate through Hawking radiation. The universe will become a dark, empty place, punctuated by the occasional flicker of a dying star. The slow death of the universe raises profound questions about the fate of life and intelligence. If the universe is destined to become a cold, dark, and empty place, what hope is there for the survival of any civilizations that may arise within it? Some futurists speculate that advanced civilizations may find ways to harness the remaining energy of the dying universe, perhaps by tapping into the energy of black holes, or by creating artificial environments within which life can persist. Others suggest that intelligence may find a way to escape the confines of our universe altogether, perhaps by creating wormholes or by transitioning to other universes with different physical laws. However, these possibilities remain highly speculative. It is also possible that intelligence, like life itself, is a fleeting phenomenon in the universe, a brief candle flickering in the cosmic darkness before being extinguished forever. The fate of intelligence in a dying universe is a question that may never be definitively answered. However, it is a question that forces us to confront our place in the grand scheme of things, reminding us that our existence, like the universe itself, is finite and precious. The story of the universe is a grand and awe-inspiring epic, a tale of creation, evolution, and eventual demise. From the fiery crucible of the Big Bang to the slow fade of the cosmic dark age, the universe has played out a drama of unimaginable scale and complexity. And we, as inhabitants of this universe, are privileged to witness a small part of this grand cosmic drama. Our time in this universe is fleeting, a brief moment in the grand scheme of things. Yet, it is a moment filled with wonder and beauty, a chance to explore the cosmos, to unravel its mysteries, and to marvel at its grandeur. The knowledge that the universe is slowly dying should not fill us with despair, but rather with a sense of awe and gratitude. We are fortunate to live in a time when the universe is still vibrant and alive, a time when we can explore its wonders and marvel at its beauty. Let us cherish this moment, for it is a gift, a fleeting opportunity to experience the wonders of the cosmos and to contribute our own small part to the grand story of the universe. As our journey through the cosmos comes to a close, we are left with a profound sense of awe and wonder at the universe we inhabit. We have witnessed the birth and evolution of galaxies and their eventual demise. We have peered into the hearts of these cosmic metropolises where supermassive black holes hold sway. And we have grappled with the profound mystery of dark matter. We are not just observers, but active participants in this grand cosmic drama. We are stardust, the atoms in our bodies forged in the cores of stars. This profound connection to the cosmos, this realization that we are not separate from the universe, but rather an integral part of it, is a humbling and awe-inspiring thought. It underscores the interconnectedness of all things, how the fate of galaxies billions of light-years away is ultimately intertwined with our own. The study of galaxies is therefore not just an abstract pursuit of knowledge, but rather a deeply personal one. By understanding the universe around us, we come to a better understanding of ourselves, our place in the cosmos, and our connection to the grand sweep of cosmic history. The vastness of the universe can be overwhelming, its timescales beyond human comprehension. Yet, it is precisely this vastness, this sense of cosmic perspective, that can help us to appreciate the preciousness of our own existence. We are fortunate to live in a time when the universe is still vibrant and alive, a time when we can explore its wonders and marvel at its beauty. Our journey through the cosmos has been a journey of discovery, but it is also a journey that is far from over. For every question we answer, new questions arise, pushing the boundaries of our knowledge and challenging us to delve deeper into the universe's mysteries. The nature of dark matter, the ultimate fate of the universe, the possibility of life beyond Earth. These are just a few of the many questions that continue to captivate astronomers and inspire a sense of wonder in all who contemplate the cosmos. The quest to understand the universe is an ongoing one, a relay race of scientific inquiry passed down from generation to generation, each new discovery building upon the work of those who came before. And as we continue to build ever more powerful telescopes and develop ever more ingenious techniques to probe the universe's depths, we can be sure that the cosmos will continue to surprise us, revealing new wonders and challenging our assumptions about the nature of reality itself. From our vantage point on Earth, a pale blue dot suspended in the vastness of space, the universe can seem like a distant and indifferent realm. Yet, it is precisely from this small and fragile planet that we have embarked on this grand cosmic adventure, using the power of our minds and the ingenuity of our technology to extend our reach across billions of light years. The study of galaxies is a testament to the human spirit, our insatiable curiosity, and our unyielding desire to understand the universe around us. It is a reminder that even in the face of overwhelming vastness, the human mind is capable of grasping the most profound truths about the cosmos. And as we continue to explore the cosmos, we carry with us the hopes and dreams of humanity, the desire to find our place in the universe and to understand our connection to the grand sweep of cosmic history. The knowledge we have gained from our exploration of the universe is not just a collection of facts and figures, but rather a source of profound inspiration and responsibility. As we come to a better understanding of the universe and our place within it, we are also called upon to become better stewards of our own planet, the only home we know. The challenges facing our planet, climate change, resource depletion, environmental degradation, can seem daunting, even insurmountable at times. Yet the cosmic perspective reminds us that our planet is a precious and fragile oasis in the vastness of space, a rare and precious jewel that deserves our utmost care and protection. By embracing the cosmic perspective, by recognizing our interconnectedness with the universe and our responsibility to future generations, we can find the inspiration and the motivation to create a more sustainable and just future for all. The universe is vast, mysterious, and full of wonder. It is a realm of endless possibilities, where the laws of physics allow for phenomena stranger than anything we can imagine. It is a realm that has captivated the imaginations of humans for millennia, inspiring countless myths, stories, and works of art. And as we stand at the cusp of a new era of cosmic exploration, with ever more powerful telescopes peering deeper into the universe's depths, we can be sure that the cosmos will continue to surprise us, challenge us, and inspire us with its beauty, complexity, and sheer strangeness. The universe beckons, inviting us to continue our exploration, to unravel its remaining mysteries, and to discover our place within its grand and ever-evolving story. The journey is far from over, but the rewards, both intellectual and spiritual, are well worth the effort. For in exploring the universe, we are ultimately exploring ourselves. As we return from the swirling event horizons of supermassive black holes and conclude this journey through the warped fabric of space-time, as we slowly drift back from the shimmering spiral arms and conclude our visual journey through the complex history of galactic evolution, if your imagination was ignited by our exploration in this space documentary, I genuinely invite you to support our mission by liking this space documentary, leaving a comment on your favorite cosmological theory, and subscribing to the Physics and Cosmos Academy to stay updated on the latest breakthroughs in general relativity, high-energy astrophysics, and different exciting topics in astrophysics and cosmology. Please, share this investigation with other curious minds who are equally captivated by the enigma of dark matter, the accelerating expansion driven by dark energy, and the hunt for habitable exoplanets. Because your active engagement is the vital force that allows us to fulfill our promise of producing more profound documentaries that unravel the majestic, mathematical symphony of our universe.